So what we're going to look at today is we're going to look at ellipses. And ellipses are a conic section, right, in which the entirety of the curve is closed, right? So it's a different kind of conic section from the parabola and from the hyperbola in that all of our points on the ellipse are within one set area. If you think about a parabola actually goes out towards infinity, and a hyperbola is going to do the same thing, but in two different directions. But the ellipse is going to be completely enclosed. And later on, we'll talk about the circle, and the circle is an example of an ellipse, a very special kind of example that has to do with its eccentricity and the special values for its eccentricity, which we'll talk about later. But for right now, we're going to focus in on this very special conic section. In particular, the ellipse is used quite a lot inside of physics, a lot inside of astronomy, right? We talk about things like elliptical orbits and the elliptical orbits of planets, right? And we model those utilizing these ellipses, and it's kind of miraculous that the movements of these huge orbital bodies actually follows a very, very prescribed orbit based upon this mathematical computation, okay? So an ellipse is the set of all points x, y, where the sum of the distance from the point to two other points called the foci is constant. So let's take a look at this ellipse, and let's imagine that we kind of separate the ellipse into four sections. Right through the center of the ellipse, the center right here, okay? And we're going to put our two foci, and for right now, that's about where the foci would be on this particular ellipse. And what we want to do is we want to think about how it is actually that the ellipse is constructed, how these points are, this line is constructed. So what we'll do is we'll imagine that we've got a string, okay? And that string, whatever length it is, what we have is we're going to have two distances. We'll call this distance 1 and this distance 2, okay? And the length of the string is distance 1 plus distance 2. Now, as I move the string over, let's say, for example, I move this string in this direction, the length of distance 1 increases and the length of distance 2 is now going to decrease. And what we'll notice is that, in fact, in terms of the vertical on this particular ellipse, that vertical is increased. Now, we'll move it again, and we can see the same thing happening, right? Distance 1 increased, distance 2 decreased. We could go in the other direction, and we could, in fact, increase distance 2, and then distance 1 would decrease as well. In this case, we get almost something that looks kind of like a right triangle, okay? We could even imagine that we go all the way around until we finally hit this point right here, and we'll give a name to that point. That point is going to be called our vertex on what's called our major axis. In fact, in addition to that, if you kind of imagine the longest vertical distance that we'll get from those two from the center to those two foci, that's going to go right through this other line here. And that is going to end up being half of the length of what we call our minor axis. And so essentially you could imagine also if we went in the backwards direction or underneath the center, you can kind of see how these points are constructed. And that's how we actually go out and we construct this ellipse. All the points are going to be constructed utilizing this basic method. So now let's actually go out and label our ellipse in order to give us a better sense of the different parts of the ellipse so that we can then go in and do some mathematics or some analysis utilizing this ellipse. So this length right here that goes right through the center of the ellipse on the long edge, this is what we call the major axis. Whether or not our ellipse is vertical or it's horizontal in terms of its long side, that's always going to be called the major axis. And our foci, they're always going to be on the major axis. So again, this is what we call a focus. There are two of them together, plural, that's foci. Now what we'll do is we'll draw a line through our center down to the highest point on our ellipse that we drew before, and this is what's called the minor axis. The middle here, again, we utilize this term, it's called the center, and we'll represent it as HK on the ellipse, or on the Euclidean plane, excuse me. These points out here, they're called our vertices, and that's called a vertex. We got another vertex over here. And now what we want to do is we want to go in and actually talk about some distances. So the distance from the center to the foci is called C. The length here from our center to the vertex, we're going to call that A. Now, something I want to notice here is, I'm going to draw a little picture. If we kind of think about this length, remember we actually could, in fact, imagine going all the way out to the vertex utilizing the definition of our ellipse. And you'll see we've got that length right there. And it's in fact, the purple part will be from the far foci, this foci right here, out to this foci, or out to, the point to the vertex. Right, so it'll go that entire distance. And then we'll utilize a different color. Let's use yellow. And this yellow part right here, that's the distance from the short foci, okay, out to the vertex as well. Now, if we were to just put that over to the other side, you could see that the entirety of the length, the purple part plus this yellow part, is actually 2A. And that's going to be really important for us. We'll talk about that in a little bit later. So this entire length, right? So the length of the string, D1 plus D2 actually equals 2A. Now, this length here from the center to the top of the ellipse, we're going to call that B. So remember how we drew B. B was when D1 and D2 were actually equal to each other. So that, if we rewrite that, that'd be D1 plus D1 equal to 2A. And so that distance D1 was just going to equal A. So that's the length right there at A. Notice also it's a right triangle, so we can utilize the Pythagorean theorem. And we can actually write B squared plus C squared, and that'll equal A squared, because that's the length of that side. So what that means is that B squared is going to equal A squared minus C squared. And that actually gives us a relationship between the lengths of all those different sides. It's actually going to be very handy for us. And that kind of generates the entirety of our ellipse. On the one hand, we have the center at HK. We'll have the minor axis, which is the short side. We'll have the major axis, which is going to be our long side. And our foci, remember, are going to be located on that major axis. Our vertices, they're also on the major axis. The length from the center to the foci, we're going to call that C. The length from the center up to the top of the ellipse, or maybe the side of the ellipse, depending upon how your ellipse is oriented, the short side, that's going to be B. And the length from the center to the vertex, that's going to end up being A. And that kind of allows us to draw the entirety of our ellipse. Now what we want to do is we want to go in and derive the formula for the ellipse. To derive the formula for the ellipse, we're going to take some pieces of information. One is we know that the distances, when we add the two sums of the distances together, that's going to end up giving me 2A. We've got our foci, and our foci, we're going to, for the sake of simplicity and without any kind of loss of generality, we're going to have these foci on the x-axis. So this foci is going to be negative C0, all right? And this one's going to be C0, and that means that our center is going to be at 0, 0. And we're going to take an arbitrary point, any arbitrary point that we want, and we'll call that arbitrary point xy. So we've got these two lengths right here. Now, we'll call this one distance 1, and we'll call this one distance 2. Distance 1 is going to end up equaling, it'll be the square root, using the distance formula, of x minus negative c squared plus y minus 0 squared. And distance 2 is going to end up equaling the square root of x minus c squared plus y minus 0 squared. So our distances added together, that's going to be the square root of x plus c squared plus y squared plus the square root of x minus c squared plus y squared ends up equaling 2a. And so now what we're going to do now is we're going to go through and we're going to derive the formula for the ellipse, the standardized formula that we use for the ellipse. This process is pretty common. It's the kind of thing that you'll do a lot inside of physics. You're going to see it a lot inside of mathematics. But if you're like, hey, I just want to know what the formula is, you can kind of skip through the whole portion right here, because it's kind of algebra intensive. So what we're going to do now is we're in fact going to subtract over this x minus c squared plus y squared. So that's going to give me the square root of x plus c squared plus y squared. And that'll equal 2a minus the square root of x minus c squared plus y squared. Now we're going to square both sides. And that's going to give me x plus c squared plus y squared on this side. And that'll equal then, and we're going to write this as, it'll be 4a squared minus 4a times the square root of x minus c squared plus y squared plus x plus, we're going to write this out as x squared minus 2xc plus c squared plus y squared. And that's just actually expanding out x minus c squared. We'll do that on this side too. That's going to give me x squared plus 2xc plus c squared plus y squared equals, right? And then we'll have just 4a squared minus 4a times the square root of x minus c squared plus y squared plus now x squared minus 2xc plus c squared plus y squared. So what we can see now is that we can actually take out the x squared. The y squared is going to go away as well, okay? As is the c squared. We'll pull over that 2xc, so we get 4xc equals 4a squared minus 4a times the square root of x minus c squared plus y squared. Now we'll pull over the negative 4a, so we'll get 4xc minus 4a squared, and that'll equal negative 4a times the square root of, again, x minus c squared plus y squared. And then we'll divide through by 4, and that'll give me now xc minus a squared equals negative a times the square root of x minus c squared plus y squared. Now we'll square both sides again in order to get rid of that last square root. And that is then going to give me x squared c squared minus 2xc a squared plus a to the fourth. And that'll equal then a squared times x squared minus 2xc plus c squared plus y squared. We'll go through and we'll multiply through the a squared. So this is going to give me x squared a squared minus 2xc a squared plus c squared a squared plus a squared y squared. Now we'll notice that on both sides we've got the xc a squared, so we could actually take those out. Okay? And now what I'm going to do is I'm going to group together my constant terms and my x terms. X and y terms, excuse me. So on my left-hand side, I'm going to have a to the fourth, and I'll subtract over the c squared a squared. So make that minus c squared a squared. And that's going to equal, this is going to be x squared a squared. We'll subtract over x squared c squared, and then plus a squared y squared. Now I can actually go through and group here. I've got a squared times a squared minus c squared equals, and then we'll have x squared times a squared minus c squared plus a squared y squared. Now remember what we did before. We actually saw that b squared was going to equal a squared minus c squared. So I'm going to change a variable here, right? We had that earlier when we constructed our ellipse. So this is going to give me a squared b squared equals x squared times b squared plus a squared times y squared. What I'll do now is I'll divide through by a squared b squared. And what I get is, just moving this over to the left-hand side, I'm going to get 1 equals x squared over a squared plus y squared over b squared. And that's how we construct the formula for an ellipse when it's centered at the origin. Same process if we're actually going to get a vertical ellipse, or even if we center the ellipse at a different place other than the origin. All right, the algebra basically remains the same. So this is the general equation for a horizontal ellipse. We'll also see that you can take x squared over b squared plus y squared over a squared, remembering that a is the length of the major axis, and equal to 1, and that's a vertical ellipse, both centered at the origin. So that's at 0, 0. Or if we wanted to, we could actually change this up and we could make it x minus h squared plus y minus k squared, okay, over, say, a squared, b squared equal to 1. And that's a horizontal ellipse centered at hk. And similarly, we could do a vertical one at hk, and that would look like this. This would be x minus h squared over b squared plus y minus k squared over a squared equals 1. All right, so that's actually how we end up with the form for ellipses, whether or not they're vertical or horizontal. So now let's use what we've learned in order to go out and graph ellipses, given the equation for the ellipse. So let's say, for example, I have x minus h squared over a squared plus y minus k squared over b squared equals 1. And that's when I have essentially what's called a horizontal ellipse. That is, the major axis is the horizontal line. Or we'll have x minus h squared over b squared plus y minus k squared over a squared equals 1. And that will be a vertical ellipse. Notice that a is always going to be greater than or equal to b. And a is the length of our major axis, b is the length of our minor axis. So we'll take this and we're going to have x minus 3 squared plus y minus 2 squared. And we'll put this over 9 and this over 4. Notice 9 is the larger of the two. So consequently, that means that we're going to have a horizontal ellipse because it's under the x. See that? It's under the x, so consequently, we'll get that horizontal ellipse just like in this first instance. So what I'm going to do, I'm going to draw my axes. I'm going to go in here, I'm going to note h is 3, k ends up being 2. So our center is going to be at 3, 2. And we'll put that there, 1, 2, 3, 1, 2, 3, 2. Now notice that a squared will equal 9, and so consequently a is going to equal 3. We'll always just utilize the positive version because we can't have negative distances, and a is a distance. Then b squared is going to equal 4, so b ends up equaling 2. So 1, 2, 3, 1, 2, 3. Our major axis has a length of 3, or actually length of 6, excuse me, and our minor axis has a length of 4. Then we will simply go in and draw our ellipse. And there we go. Now, we may also want to find our foci. So remember that a squared minus c squared equals b squared. So consequently, what we get here is we're going to get 9 minus c squared is going to equal 4. That'll give me negative c squared equals negative 5 when we subtract 9 from both sides. So c squared equals 5. So c is going to equal the square root of 5. And that's just slightly larger than 2. And so there will be our foci. We'll have them just be basically right about there. So there's our foci. And there's our ellipse. So we go in, we'll find the center of the ellipse, x, or h and k, excuse me. And then we'll find a squared, b squared. A squared is going to be the larger of the two. And we'll dictate whether or not we are going to have a horizontal ellipse or a vertical ellipse, right? Which one's going to be longer or shorter. And then that'll give us a and b. And then if we need to find our foci, what we'll do is we'll go in and we'll use a squared minus c squared equals b squared to find what c is. Remember that our foci are going to be along the major axis, right? So our major axis here is that length right there. And so consequently, make sure you put your foci in there. And that's how we go out and graph an ellipse. All right, so now let's take a look at another example. Let's say, for example, we have x minus 4 squared over 25 plus y plus 1 squared over 49 equals 1. So what we'll do first is we'll examine and we'll see that under the y, we have a larger value under y, and so consequently this is going to end up being a vertical ellipse. My major axis is going to be vertical. So first we'll notice that HK, our center, is going to end up equaling 4, -1. And that's because, remember, it's y minus k, so k is equal to -1 in this case, so we get 4, -1. A squared will equal 49, because it's going to be the larger of the two, so a will equal 7. And b squared is going to equal 25, so that means that b is going to equal 5. Now we'll go ahead and find c so that we can put it in our foci, because that might actually be really important. So remember that a squared minus c squared is going to equal b squared, so that means 49 minus c squared is equal to 25. That's going to tell me that c squared is going to equal 24, so c is equal to the square root of 24, which is equal to 2 root 6. So now let's go through and we'll draw our graph. First, 1, 2, 3, 4, -1. So there's the center of our graph. Our major axis is going to be up down, so it's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That's the length of A. And then we'll have the length of B is going to be 5, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And there we go. There is our ellipse. Now, 2 root 6 is just a little bit more. It's almost 5. So 1, 2, 3, 4, 5. Right about there, a little bit less than 5. 1, 2, 3, 4, and 5. A little bit less than 5. And there is our foci. And that's our ellipse. So we go in, we find the center, we determine which one's larger, under the y or under the x, and then the larger one will become a. So we take the square root of whatever that value is, and then we'll take the square root of whatever the value for b squared is, and that'll give me a and b. We'll draw the center, we'll find our major axis, draw out to the major axis, draw out to the minor axis, place our foci, and that gives us our ellipse. And so that's how we go out and draw them. So what are the key things that we want to remember from this video? One, remember what an ellipse actually is. That is that it's all of those points that are equal to the sum of two lines coming in from the foci, right? So it's kind of like that drawing that we did around the ellipse. In addition to that, you need to make sure that you know your equations for the ellipse and how to utilize those equations in order to graph ellipses on a Euclidean plane. That completes our first lecture on ellipses. We'll actually be talking more about eccentricity, how do we utilize completing the square, and some other topics inside of ellipses at a later video. This is Dr. George Sweeney, and I want to thank you for watching my video. If you found it helpful and you liked it, go ahead and click the thumbs up. If you want more of these videos and you want to get my updates, please click subscribe. If you have any questions or you just want to say how much you really enjoyed the video, go ahead and leave some comments. I do read and respond to the comments.